So we begin our lecture, and this lecture will resume all the previous material, in the sense that we have passed a lot of new concepts and methods. So it is better to repeat now the general concept of the material exposed before. So let us begin from the configuration of logic gates. So that is the Boolean functions. First of all, it is NAND, yes? That is not AND. The universal function, Boolean function, which generate all possible other logic function. With such simple configuration of the neural net. So we have only one neuron with the bias 3, with the weight coefficients -2, -2, x1, x2. Then we calculate the weighted sum, shifted weighted sum. Yes, -2 x1, -2 x2, plus 3. And we have some output z, and then we have transform of the output z. The sense that we apply the function, the cutting function. The cutting function in the sense it cut us to 0 all the values smaller or equal to 0, and if z positive, it will be 1. So we can see that the table of NAND verifies. So 0, 0, the result 1, 0, 1, 1, 1, 0, 1, and 1, 1, 0. So not AND. And using this configuration of neural net, we can construct now any Boolean logic function, for example, or. So we have the summation of two input, x1 and x2. We have the sum x1 plus x2 plus in circle means that it is the summation by model 2, yes, and we also elaborate the carry bit by simple multiplication of x1 and x2. So, and other Boolean function we can also construct by means of such important element in analogous way. So, the basic example of our problem to use the neural net is the problem of classifying handwritten digits from the American MNIST data set. Yes, so it is handwritten sample is 50,000 examples of handwritten digits, and 10,000 it is for 50 or 60,000 for training of our neural net, and 10,000 for verification. So we should verify this sample for verification, which have not passed the training process. So, and very interesting thing that we, up to now we have considered only the complete connected neural network. So any neuron is connected with all other neurons. Yes, so we have complete connection scheme. So fully connected to each other. Okay. So we have input layer. Yes, it is pixel of our MNIST dataset. And we have our 10 output layer, which corresponds to the weight of recognition. So it is probability to be certain symbol. Then we studied the methods to train this neural net learning. So first of all, we told that we should learn our network with gradient descent method. It means that we firstly choose some so-called cost function, and this cost function will be the criterion of our training. Okay, cost function in such form written is the mean square error between the result of our neural net and the desired result. So we have this summation by all training samples, and we should create this cost function, which depends on all weights in the network, all the biases in the network. Yes, Y is the desired output and the total number of training inputs. And A is the vector of outputs from the network when X is in input. Okay, so it is the real result of our network. So the aim of our training is to minimize the cost, that is to minimize the mean square error. So C of WB should be brought to minimum by W and P parameters as a function of weights and biases. Then, when we impose this problem, yes, state this problem, the gradient descent update rule in terms of components will be WK. We'll substitute WK prime is WK minus eta, the derivative of C by WK, and the same update rule for the biases. For any layers, for any neuron inside this layer. And eta is the parameter called speed of learning. So for some small fixed epsilon, positive but small as small as we want, we define eta like epsilon divided by the norm of nabla C. Nabla C is the vector of all partial derivatives dc by dwk and dc by dbl. So such very long vector, yes, and the norm means the Pythagore length of this vector. So this square root of the summation of square of the quadrats of components. This. So stochastic gradient descent. Now our problem is to minimize our cost function. Stochastic gradient descent. Now we want to accelerate the procedure of our training. So we don't want to train using all data set, which is very big, yes, and so to adjust a lot of parameters. But we want to choose randomly. We want to choose randomly some subset of our training samples of small volume, and we shall refer to them as mini batch. Of course, the procedure to choose mini batch should be random, well mixed procedures. Well mixed in the sense that we have a uniform distribution of random choose of our mini batch in the training cell. So choose the sample size M large enough for which the average by our mini batch, the gradient by mini batch approximates the value of our gradient of our function. That is the summation of by our mini batch and averaging by M mini batches is approximately the summation by all training sample x of gradient Cax. Also divided by n. N is the number of our training set. It is 60,000. So we can abbreviate it. And it is we think that it is approximately equal to our gradient of C. So we can expect that gradient of C is can be approximated by the medium value by mini batch samples. So it can brief our procedure, for example, 60,000 times can brief. So we can estimate the overall gradient, yes, which we tend to find to bring to the minimum, yes, to near to zero in ideal case, and we can approximate it just using the randomly chosen mini batch. Returning to our task, now we can rewrite the updating procedures, our recursion procedures, like WK will be substituted by WK minus eta divided by M summation DC xj by WK. So our gradients by the weight parameter, and the same thing will be update to update our bias as all the nodes of our network. Where the sums are all training examples in the current min batch. It can brief our procedure 60,000 times. Then, in order to evaluate now the partial derivatives of the cost function, we considered the backpropagation algorithm in the following way. So we introduce a new parameter. It is the error function of neuron J in layer L. So considering any layer L in our neural net, we can estimate the error function of neuron properly by considering the gradient of cost function, respectively to the corresponding parameter zeta JL. And we take it like error of the neuron. And there is some motivation, we considered it. There is some motivation to choose such error function and then to evaluate all our gradients through this error function. Our lecture today is devoted to all the precedent material, and we resume all we have considered before. Okay, it is some resuming lecture. So the backpropagation is based on 4 fundamental equations. Evaluation of delta L, so it is the error of output layer, yes. Evaluation of output layer, then evaluation of any layer in this evaluation of the error parameter in any layer L, yes. And then the expression of gradients for the variables, our biases and weight parameters, yes, of the cost function, which is our aim. So our aim is to find the value in the backpropagation free equation and in backpropagation form. But we do it through the evaluation of delta L of the last layer, so output layer, and of any other layers. Here the circle multiplication is defined like element-wise product of 2 vectors, so-called. It is element-wise product, so 2 vectors, 1, 2, 3, 4 is the corresponding components will be multiplied. Now, let us summarize the propagation algorithm. First of all, we consider the input X. So we set the corresponding activation A1 for the input layer. Then feed forward, yes, we begin to propagate the forward for each new layer after first layer input, second, third, and so on. And L capital means that the output layer compute the weighted sum shifted by the corresponding bias, yes, in the layer, and to compute the activation parameter AL. It is the activation function sigma in the point zeta L. Yes, this weighted sum plus the shift. Then compute the vector error, output error. Compute the vector delta A nabla A C. Then this component-wise multiplication sigma prime in the vector zeta L. So the value zeta L. Then, but having this error of the our output layer, we can now backpropagate zero. We can now to compute the values which permit us to correct by recursive procedure to correct the coefficients of this network. This training means that we should correct our weight coefficients and bias coefficients to minimize as possible our cost function. Okay, good propagation is the formula delta L is W L plus 1 transposed multiplied by delta L plus 1, it is error parameter. Then this multiplication by delta by sigma prime, yes, it is the derivation of our activation function. And output, the gradient of the cost function is given dc by dw by weight coefficient and dc by db jl by bias parameters. Then, in order to avoid the problem of training procedures, which we can the speed of our training procedures can decrease dramatically, and our procedures of the next training will have not a sense. And the quadratic cost function, unfortunately, have the following properties: that its gradient respectively to the weight parameter is A multiply activation value multiplied by sigma prime of z. So here enters the derivation of our sigmoidal activation function. And the shape of this function is sigmoidal. And we can see that near zero, the behavior of such function is very good. But after 4, before -4, its derivation, become near to 0. So the gradient is very, very small. And that is the motivation why in these special neurons, the network doesn't train at all. So when the derivative can become very small, because our value z belong to the domain of small derivation, small value derivative. Our neural net finished to do the procedure of effective learning. But we can avoid this problem by considering the cross entropy cost function, which have some logarithmic form. And it is very similar to the probability cross entropy, but not properly, because probability has always the normalization of by 1, the formula of complete probability. But here we have some generalization of entropy function without normalization, probabilistic normalization. So we have such expression of our new cross entropy cost function. Okay. And its total number of items of training data. The sum is over all training samples X, and Y is the corresponding desired output, and the activation function is always sigma of Z. So it is logistic, so-called logistic function. Yes. 1 divided this sigma. 1 divided by 1 plus exponent in the power minus z. And this function is also cost function, because when A and Y are near by their values, C tends to 0. So our aim is to make the value A, yes, real result of our neural net, and Y is desired value. Really, it vanishes the cost function. So it has all the properties of cost function, but there is some property more. By the form of this cost function, we can cancel the presence of derivation of sigma of z, because we have this special function. So taking the partial derivation, we can cancel in numerator and denominator. We can cancel the same terms sigma prime. So it doesn't depend more on sigma prime. So are reduced after calculation, and so we don't depend, and we have no more the pathological case, not possible to succeed, that the gradient of our cost function by the parameters of weights and the parameter of biases can be very, very small. It was reasoned for the simple configuration of our neural net. But now we can extend this mathematical formalism to many neural multi-layer networks by considering this summation. Yes, or summation of J over all output neurons, and summation by X by all training samples. Yes. So such generalization avoids a learning showdown in many neural networks. Then very, very interesting thing is to substitute the last layer. The last layer is the output layer. To substitute the traditional sigmoidal activation function by softmax activation function. But it is only for one layer, the last layer. It is only for the output layer. And the idea of softmax is to define a new type of output layer for our neural networks. So it begins in the same way as with a sigmoidal layer, but by forming the weighting input like before, yes, that JL is the last, it is the weighted sum of the output from the precedent layer, yes, plus the corresponding biases. In any neuron. However, we don't apply for the last layer. We don't apply more the sigmoidal function to get the output. Instead of this, we apply other function. It is softmax function AJL. It is exponential. Exponent in the power zeta JL divided by the summation of exponents zeta KL by all k. Yes, by all neurons in the last layer L. Okay, and such transformation, such strange thing that we apply to the last activation layer of neurons, softmax activation function can essentially improve our training procedures. it has been found occasionally, not regularly, but it works very good, and it can be adjoined to the instrumentation for good training of neural nets. The other cost function can be log likelihood cost function. There are some probabilistic reasoning why to use the logarithmic likelihood cost function, and it is very good cost function. Also does not depend on the derivative of the activation function of sigmoidal, but only on the difference between the value of the output neurons and the desired value of our training set. So it is very good cost function. Then we considered the problem of overfitting and regularization. And overfitting and regularization is now absolutely obliged procedures. Regularization parameter and some regularization of L2 or L1 type are very necessary in all real situations. So what we do to regularization? We only adjoined some summands. It is really some square mean square value of our weight functions, of all our weighting functions. But W by all weighting function present in the network. Okay? So we can consider a matrix of all weighting function. Matrix function we can present like some lines or columns, yes, like a very long vector, and we make some summation of squares divided by 2n and multiply on some coefficient lambda called so-called the regularization coefficient. The gradient descent learning rule for the biases doesn't change from the usual rule, because you see we have adjoined only the weight parameters. So for the derivation by biases, it is constant, so it doesn't affect. But for learning rule for the weights, it become contain some correction terms, and this correction terms is very important for overtraining procedures. It saves us for this. So we can take the summation of squares of weights. It is L2 regularization, and we can also use the summation of the absolute value of W. It is so-called L1 regularization, because it is L1 and L2 matrix of the space, of Rn space. So if we differentiate the formula for regularization L1, we have dc by dw is dc0 by dw, so our traditional term, plus lambda divided by n signal w, where sigma signal is the sign function, this step function, and the update rule for weight become some correction for the for lambda, our normalizing coefficient L1, and for biases doesn't change also because it doesn't depend on the biases. Then also very interesting thing, dropout regularization. Here we randomly exclude some neurons from our consideration, and we begin to train only a part of our neural net. And after the training, so every iteration procedure, we change the presence and absence of different neurons in our given layer. And after this procedure, we take some middle value of the corrected parameter, like weights coefficients and the bias coefficient by our normal methods of gradient descent and backpropagation. Such technique reduces the complex co-adaptation of neurons, since a neuron cannot rely on the presence of certain neighbors. So when we need to avoid the influence of neighboring neurons in some specific problem statement. Okay. Then a very important thing is how can possible to enrich our training set. And the method is artificial expanding of training data. So having 60,000 training samples, we can transform such images, for example, rotating in a little by 15 degrees, but not only, by different value of degrees. We can rotate, then we can shift inside the box of a little box, and then to modify the handwritten image by simulating some tremor of hands of some person, and so on. In this, by this simple transformation, which we can arrange automatically, we can obtain from 50,000 or 60,000 data set. We can obtain millions of samples, different enough. So we can enrich and to improve the precision of our training. Then we also consider the neural net universality theorem, or why neural nets can compute any function. So let us take any function. Now we can reveal what is some polynomial trigonometric function. And the output of the network will be, as usual, yes, sigma, yes, activation function of summation of aj, wj, weighted sums of the output of our neurons, plus the corresponding b bias of the output neuron. So the solution is to design a neural network whose hidden layer has a weighted output given by sigma inverse applied to our function f of x, which we need to calculate. Okay, so the weighted output should be now we transform our function f of x by the inverse of our activation function sigma, yes, 1 divided by 1 plus f exponential minus z. And we have now such shape of our modified function. The solution is we can consider a neural net specially built for this approximation, and it can approximate by rectangles our shape of our function, and the width of our rectangles can be as small as we want. So it is very good approximation. It is some analogous of integrals sums as such. Then also one can observe the vanishing gradient problem. So, for example, considering the recognition of high hand-written digits, let us consider now neural net with 28 by 28, yes, 784, 30 hidden neurons, yes, one hidden layer, and one output layer 10, yes, from 0 to 9. And using our normal procedures with normalization, with the cross entropy function and so on. So with all prevention of problems of learning, we can reach the classification accuracy of 96 or 48. Then let us now adjoin a new hidden layer of 30 neurons, and we have some slight improvement. But if we adjoin other layer, we have a drop of our accuracy, and adjoin one other, yes, we have also a slight drop of accuracy, and by adjoining new hidden layer, we always have some drop of precision. So by adding another hidden layers, the systematic deterioration is observed. And it is it is very universal phenomena for all complicated neural net. Why it happens? So we have, for example, hidden layer 2 and hidden layer 1. And here the bars, the logs of bars are proportional to the gradient dc by db for each neuron. Okay? So we can see that this essential long of the bar, the neuron, this neuron can learn very good. But when we have some gradient near to 0, this neuron doesn't learn at all. So this is a problem. And why it happened? It happened because, for example, for four neurons, we have only input, then second so hidden layer are only one neurons. Hidden, then hidden, then hidden, then output. We have multi-layer, but any layer consists of only one neuron. And we have the expression that the gradient C, respectively dB, the first bias, is, you see, sigma prime of Z1, then W sigma prime Z2, and this is by the construction of our sigmoidal activation function. This term should be strictly smaller than 1/4. And this also strictly smaller than 1/4. That is why this is the exponential function, yes, 1/4 in the power n, and n is number of new adjoint layers. So it is absolutely normal that it should be decreased to 0. So we should keep it in mind that such situation can, on the contrary, can succeed also the inverse problem, which is the problem of exploding gradient problems. For example, let us put now W1 equal to W2 equal to W3 equal to W4, 100. Wait. Fine. So, and we know that if Wj is equal to 0, so sigma prime in 0 equal to 1/4 by definition of sigmoidal function. So, for example, we want zeta1 is equal W1 A0 plus B1 is equal to 0. So we have B1 equal to minus 100 multiplied by A0. So 100 multiplied by the maximum 0, 1/4 is 25. And we have consequently, you see, multiplicand with the value 25. So it is exponential explosion of the value. Okay, this is all what I wanted to resume. It is the basic thing that we considered precedently. The following lecture will devoted to so-called the convolution neural network. And what is a convolution neural network? It is very clever configuration, but before we dealt with only, you see, dealt with only fully connected neural net. So any layers are interconnected by its all neurons. Yes, every neurons connected with other neurons. It is very good for begin to study and begin our backpropagation and so on. But in real situation, it is not the best configuration of the network. So next we will split our topology of neural net into some models, and we have not more the configuration of total interconnection of all neurons, and not necessary. And we can then to make some confrontation between the fully connected network and some special convolutional network with for the criteria of efficient. But if we have some subclasses, yes, some clusters of our connections of our network, the backpropagation and the gradient descent technology will function as before. Only we should summarize our results not by all connections as before, but only by the cluster of connections. So we can reduce only our summation, but we can reduce also the complexity of our elaboration of and training procedures. And it can be simplified and even to increase the precision of our neural net. It's very good thing. It is so the next tomorrow I will tell about the convolutional network with some clustering of the configuration of the network. And it is very important. Why? Because we can parallelize. We can use some tensorial calculus, tensorial flow calculus technique, when we can parallelize the processes and to calculate some branch independent on other. So we can accelerate the procedure of, and for example, for graphic coprocessors, for graphic acceleration, it is very important thing. And the next Thursday, the last lecture, I try to introduce the transformer, so-called transformer technology. Transformer in which sense? In the sense of complex classification of input flow. So we have some sequence of our data. For example, automatic translation, automatically by Google. We have some words, for example, in Chinese, and then we should translate it into Italian. So we should use this processing the input flow and to produce some output flow as near as possible to the good example of something like this. So this fully connected network was very important in order to study the procedures of gradient descent and the backpropagation corrective procedures for the parameter of our network. But now we use the clustering network like more practice instruments. So it is, I think, at this point, do you have some questions? No questions. So let us finish for today.